Let's do a quick review of Newton's laws of motion. All right. Now I've created a split in the page because we're going to describe Newton's laws two different ways. One, we'll call the old way. Two, we'll call the new way. We used to refer to the law of inertia in these terms. We said an object in motion likes to stay in motion, and an object at rest likes to stay at rest. So, if this object's zipping along to the right, its tendency is to maintain constant velocity. And notice that statement also would apply to an object at rest. If an object is at rest, it has a constant velocity equal to 0. Okay, Newton's second law, we first said it fairly simply as F equals ma, but we amended that and made note that force is a vector that always points in the same direction as the acceleration vector. But it's rarely a singular force acting on an object that produces the acceleration. Generally, many forces add together and sum up, and we refer to that as the net force. And even then, it's only the net external forces that contribute to the acceleration of an object. Lastly, Newton's third law, you might have heard it stated that for every action there's an equal and opposite reaction. Might be better to say that all forces come in pairs. So what we mean by that is if object A exerts a force onto object B, and simultaneously object B exerts the same magnitude force back onto object A, these forces are vectors, and the one vector points in exactly the opposite direction of the original vector. Okay, so what's the new way to say all this? Number one, slightly different. Instead of saying objects tend to maintain constant velocity, we'll say objects maintain constant momentum. And momentum being an object's total quantity of motion. In other words, momentum is that vector quantity that's found by multiplying an object's mass times its velocity. Of course, this is all in the absence of any net external force, right? When there is no net external force on an object, it will maintain constant velocity. That's equivalent to saying when there's no net external force acting on an object, it will maintain constant momentum. Number two, this one's a little bit trickier. F is equal to the time rate of change of an object's momentum. Okay, so what's so tricky about that? Well, if we've defined momentum as the product of mass and velocity, then we'd have to use the product rule to properly take this derivative. So let's do that. Force would therefore be equal to mass multiplied by the time rate of change of velocity plus velocity multiplied by the time rate of change of mass. This is a term we often take and set equal to 0. Not in all cases, but in most cases. So then we're just left with F equals m dv dt, and we recognize dv dt as acceleration. So in the end, it's equivalent to F equals ma. But this is actually the language that Newton used when he developed his laws of motion. All right, lastly, if two objects, A and B, collide with one another, then a pair of forces such that F of object A acting on object B is equal and opposite to the force of B acting on object A. Keep in mind, there's only a singular amount of time or a single value of t for which that collision can take place. So if we multiply that value of t on both sides of the equation, what we have is the impulse delivered onto object B is equal and opposite to the impulse delivered to object A. Furthermore, we know that from the Impulse-Momentum Theorem, impulse equals change in momentum. Oops, we lost our page. Let's get that back. There we go. Okay, so if the impulse delivered to object B is equal and opposite to the impulse delivered to object A, then the change in momentum for object B is equal and opposite to the change in momentum for object A. Well, add to both sides of the equation, and we find that the change in momentum for object A combined with the change in momentum for object B is equal to 0. Or better yet, the overall change in momentum for the system is equal to 0. When a quantity for an entire system, or better yet, the change in quantity for an entire system is 0, that's saying that that quantity remains constant for the system, and that's the nature of the conservation law. So in a way, Newton's third law is equivalent to the law of conservation of momentum. All right.